this session is about the product rule for differentiation. Well, we need to start the session by stating the product rule for derivatives. That is, the derivative of a product or a multiplication of functions, u of x and v of x, is u of x times v prime of x plus v of x times u prime of x. We really want to think of this as the derivative of two functions. A first function times a second function is equal to the first function times the derivative of the second, and then the reverse of that, we add the second function times the derivative of the first. Now, many times we'll write this without the of x notation just to make it easier for us to read. You see, here's the same formula, except we see without the variable x written in. So once again, the derivative of the first function times the second function is first function times derivative of second plus second function times derivative of first. As well, we occasionally will see, and of course most of the time this is what we'll see, is we'll have a function maybe called f of x, and that function will be the product of two functions u and v, or a first part and a second part. And so then to find the derivative of f, once again it will be the first expression times the derivative of the second plus the second expression times the derivative of the first. Now, it is important to notice what this does not say, and that's very, very important, that if we have a function that's made up of a product of expressions, we do not find the derivative by finding the derivative of the first and multiplying it with the derivative of the second. It's much more complicated than that, and we cannot use this idea, so let's be very careful of that in the future. Well, what I'd like to do is, in fact, illustrate that that idea does not work, that if we want to find the derivative of a product of functions, and of course normally we wouldn't see something this simple, but in this case, let's experiment with the idea of finding the derivative of this function f by simply looking at the derivative of each expression. And of course, the derivative of 6x cubed would be 6 times x squared. And the derivative of 5x to the fourth would be 20x cubed. And you can see, of course, if we simplify that, we would get what? 120 x to the fifth. Well, really what I want you to recognize is this is not correct, and we'll scratch that out right now. This is not the way we do a problem of this nature. Now, what we do know absolutely is we could actually rewrite this function f of x as, let's see, 2x cubed times 5x to the fourth would be 10x to the seventh. And then if we were calculating the derivative of 10x to the seventh, then we would get, what, 70x to the sixth. That is, 7 times 10 is our 70, reduce the power of our exponent by 1, so we get x to the sixth. And we're absolutely sure this is correct because we know exactly how to take the derivative of this function. And clearly there's a difference here. Now, what I'd like to do, and this is simply to illustrate the use of the product rule for derivatives, is let's look at an example where we're using this product rule. And here I have this product rule stated so it's easy for us to identify. So we would first say, okay, we need to know what u is. Well, u, of course, is the first function that we have here, 2x cubed. And we need to identify the v, and of course v is the other expression we're multiplying with, and of course that's 5x to the fourth. Now, we see that when we use the product rule, we're also going to need to know the derivative of v and the derivative of u. So let's come down here and let's calculate that quickly. U prime, clearly, is 6x squared. And v prime is 20x to the third. Now, to use the product rule, we would put these items in. Let's look at the derivative of f under these circumstances. And of course, finding the derivative says take the first function u, which is 2x cubed, and multiply that with the derivative of the second function, that is v prime. Well, that's 20x cubed. And then add to that the second function v, which is just 5x to the fourth, and then times the derivative of u prime. Well, of course, the derivative of u is 6x squared. As we simplify each of these, 2x to the third times 20x to the third is 40x to the third. And 5x to the fourth times 6x to the second is 30. Well, I see I've made an error here, haven't I? So we need to be careful. I've made an error. Let's see if I can erase this and start a little back here. Let's see, 2x to the third times 20x to the third was 40x to the sixth. And then, of course, here we have, what, 30x to the sixth. And, of course, 30x to the sixth and 40x to the sixth is 70x to the sixth, which, of course, matches what we knew was absolutely correct because we knew how simple the function really was. And you can see there's a big difference, of course, in these answers. So although we may not have realized that we would get the same result, you see that we do, and this is just some kind of verification of the product rule. Obviously, we would never see a problem that looked of this nature that we're doing for our work, but this illustrates the point I'm trying to make. Also notice as I did this, I put the derivatives of each of the function in brackets. And it's probably a good idea to do that, as you'll see that's what we'll continue to do. Later on, it will help you go back and check your work because you'll know where pieces came from. So next we'll look at an example that's a little more involved. So let's prepare to do that. Okay, the next example, or the first real example for the product rule of derivatives, is stated as you can see up here at the top of the page. Find f prime of x, the derivative of f, if f of x is equal to the polynomial 2x squared plus 3 times the polynomial 4x squared plus 3x. It's going to be our challenge in the future to recognize when we need to use the product rule, and when we do, what are the functions u and v, or the first function and the second function. Well, it's pretty clear in this example, I think, the way we would write down the first function and the second function. Of course, the u is going to be 2x squared plus 3, and the v is going to be 4x squared plus 3x. So we have a little difficulty in making that decision. Now, once we've identified the u and the v when we're working on a problem using the product rule, we recognize that we're going to also have to know the derivative of each. And so that's what I've shown here. If u is 2x squared plus 3, then of course the derivative of u is 4x. That is 2 times the coefficient 2 times x to a power 1 less than 2, of course that's the first power, plus the derivative of a constant. Derivative of a constant is 0, so we're in with just 4x. Now if v is 4x squared plus 3x, then the derivative of v would be 2 times 4, or 8, x to the first power, that's 2 minus 1, and then plus the derivative of 3x, well the derivative of a constant times x to the first power is just the constant 3 in this case. Once we've identified u and v and determined the derivatives of u and v, then we simply place those into the product rule formula. So as you see here, we have u in this place and v prime here, and then we have, of course, v in this spot and u prime here. Now we could have done this, and I'd like you to try to practice this, that we may not even need to put the step that we have here in the middle. When we're going to find the derivative and we have a product, remember the way we read this is the derivative will be the first function, so we look up here and see here's the first function, we write it down, times the derivative of the second function. So we look at the second function and we mentally calculate its derivative and write it in. Then we say plus, and then we reverse those roles. The second function, so we look up here at the second function, write it down, times the derivative of the first. We refer back to our function and look at the first function and calculate its derivative mentally and input it here. That's the way we'll probably try to approach these later on. Well, now we see that we probably can do a little simplification. That is, we have a couple of binomials we can multiply together. Here we have a binomial and a monomial to multiply together. So we simply do that. 2x squared times 8x, of course, 16x cubed. 2x squared times 3, of course, 6x squared. Then we have 3 times 8x, which is, of course, 24x. And 3 times 3, of course, plus 9. In this case, we have the simple monomials, so we'll say 4x times 4x squared, 16x cubed, and finally 4x times 3x is plus 12x squared. And then we notice that we have some like terms that can be combined. 16x cubed plus 16x cubed, of course, is 32x cubed. We'll continue that process. We'll get our 32x cubed. We can combine 6x squared and 12x squared to get 18x squared, and then of course we have 24x plus 9 as the rest of our polynomial. So our final result you can read here. Now, this, in the spirit of this problem, is to learn how to use the product rule. And when you're doing problems out of your book, there's going to be problems of this nature where you're encouraged to use the product rule. Now, I think that all of us recognize that this may have not been the most efficient way to actually find the derivative. And what I mean by that is our original function is a function that we could have actually expanded before we did anything else. That is, f of x is really 8x to the fourth plus 6x cubed plus 12x squared plus 9x, which is what we get when we multiply these two binomials together. And once we recognize that this is the function f, then we could have very easily found the derivative of this polynomial by using just our normal polynomial differentiation. 4 times 8 is 32, x to a power 1 less than 4, of course that's x cubed. 3 times x, 18, x to a power 1 less than 3, of course that's 2. 2 times 12, 24, x to the first power, and finally when we take the derivative of 9x, remember we just get 9. So you notice that we have exactly the same results. This probably was a little easier for us to do, but that's not really in the spirit of what we're trying to accomplish. On a day-to-day basis later, this is what I would expect you to do. But to practice the product rule, I would like you to do this. Now, our next example will be one in which we cannot do it in a way other than use the product rule. We won't have polynomials that we can multiply together. Before we get started on this second example of using the product rule for derivatives, let me remind you that you can always pause the video. You can pause the video so that you can write down the problem completely, or you could work ahead in the problem. So use it as a tool that best fits your needs. Now, as promised, in this example, we have a function f of x equal x squared times sine of x, and we're to find the derivative of that function, but we can't do any multiplication ahead of time. We're required to use the product rule for derivatives. We have no other choice in this example. So again, it's important for us to realize the two functions that we're talking about. This is our u function, or our first function, and that's really what we mean is our first function. We're labeling that u in this case. And of course, the second function is the function sine x, or the expression sine x. So we're thinking u and v, or first function and second function. So if we approach this as we did a moment ago, we might label u as x squared. And then of course we know that we're going to need to calculate the derivative of u as we go further, so we'll go ahead and do that. And of course the derivative of x squared is 2x. We also know that we'll need and have identified our second function, and we call our second function v. So v is the sine of x, and we remember from earlier that the derivative of the sine function is the cosine function, so v prime is cosine of x. Well, once we've are to this point, well, now we're in a position that we can provide the information for the product rule. So we f of x, of course, then we can read directly is u times v prime plus v times u prime. Now, I'm going to practice what I was speaking of earlier, and we've got this that you can refer to, but the way I think about this, and the way I'd like you eventually to, is to think, oh, the product rule says take the first function, which is x squared, and multiply that with the derivative of the second function. Well, the derivative of sine of x is cosine of x. So I show my derivative, as I mentioned earlier, in brackets. And then I add to that just the reverse. The second function, which is sine of x, times the derivative of the first function. Well, my first function is x squared, and its derivative is 2x. Now, the only thing that we might look at here is rewriting this a little bit, and of course at this point those brackets aren't helping a great deal. As we get more complicated problems, then we'll see that that does help a little more. But in this case, the brackets can be removed from this first term, so we'll just write this as x squared times cosine of x. And then we have plus the sine of x times 2x. Now, it's traditional to write this monomial factor in front of the trigonometric function, so we'll write that as 2x times sine of x. And we've completed our problem. So we should be happy with that. Well, example 3 is another example of the need to use the product rule, and in fact we have, again, no other choice but to use the product rule. Well, here we have the function y equal 3x to the 4th times e to the x, and we're to find dy dx, which was, of course, the derivative of y with respect to x. Now, I've rewritten our product rule over here on the right in terms of y's. We didn't have that written originally. We had just the product of the derivative of a product. But a lot of times this is what we'll see, and we understand that this is the way that we ask for the derivative. And it's exactly the same formula that we had before. I might also add before we get started that although I've written this for our reference, it's my suggestion that you write down the product rule and recite it as first times derivative of second plus second times derivative of first. You recite it as you write it every time you're going to use it, and before you know it, you will have it memorized and you will have no difficulty with it in the future. But in the beginning, it's a little tough to remember, and you may have to refer occasionally. Well, as we get started, it's as we had before. We've got to decide what we're going to call the first function and the second function. And I suppose we could call the first function 3 and the second function x to the fourth e to the x, but we're not going to be able to get much mileage out of that. So I think it's probably normal, and you'll agree, that we'll call this the first function. That's our u expression. And our second function, of course, is just e to the x. Now, as we have done before, and we'll do once again, we label, that is, we know that we're going to need, so u is going to be represented with 3x to the fourth, and v, of course, represented with e to the x. And we know to use the product rule, we need the derivatives of each of those, u prime and v prime. And of course, it's very easy to calculate here. 4 times 3 is 12. X to a power that is 4 minus 1, which is 3. Now, we have to remember in the case of e to the x that the derivative of e to the x is simply e to the x. It's not a typo when we do this. We've got to remember that's this very special function whose derivative is identical to the function itself. Well, here we're ready to go then. Now remember, we're not talking about a function of f, we're talking about a function in terms of y. So as we write down the derivative, we'll say it's the derivative of y with respect to x. Of course, many times we refer to this as just dy dx. Okay, we have our reference. I'm going to try as I did the last time. I'm going to think first function, which is 3x to the fourth, times the derivative of the second function. Well, the second function is e to the x, and its derivative is e to the x, plus the second function, which is e to the x, we see from above, times the derivative of the first function. And since the first function is 3x to the fourth, its derivative is 12x to the third. And then we try to just clean this up a little bit. See, this is a little difficult to read, but really what we're needing to do is remove the brackets, so we get 3x to the fourth times e to the x, and as we did in the previous example, it's normal to put this polynomial, this monomial polynomial in front of, as a factor in front of the e to the x. We'll write this as 12x to the third times e to the x. Now you might notice that we have two terms and there are some common factors. Now it's not necessary to factor this result. This is exactly the result that we could be happy with. But occasionally the book or occasionally a tutor will show you to factor this. And I'd like to point out that factoring normally we do to accomplish some other task. Factoring is not necessarily simplifying. For the sake of just factoring for the sake of factoring, we usually don't do. But let's go ahead in this example and look at what would happen if we did factor it, just so we would see that it would look a little different and we can make that accomplishment. We see 3 is a factor of both 3 and 12, so 3 is a common factor. We see x to the fourth appears here, x to the third here, so x to the third is a common factor. And of course, e to the x appears in each term, so e to the x is a common factor. And we know that we'll have, of course, two terms in our parentheses, since we have two terms here, and we'll need an x in the first position, so that when we say x cubed times x, we'll get the x to the fourth that we have above. And of course, in the second term in these parentheses, we'll need a 4 so that we have 3 times 4 creating the 12. We already have the x cubed and e to the x factors, and so this is what our factored form would look like. Either of one of these answers would normally be acceptable. this problem, we're doing a little more than just finding derivatives. You can see that the problem is stated, find the equation of the line tangent to the curve y equal 2x e to the x at 0, 0, which of course we interpret 0, 0, or the origin is the point of tangency. We're looking for the tangent line that is tangent to the curve at 0, 0. Now, we remember generally, and it doesn't have to do necessarily with tangent lines, we're asked to find the equation of a line. Happens to be a tangent line, but we remember to find the equation of a line, there's two important pieces of information we have to have. We have to have a point that is on the line. Okay, well, in this case, since we have the tangent line going through the point, or tangent at the point 0, 0, we know that the point 0, 0 is both on the curve and on the tangent line itself. So we have the given point, we have the needed point. Now the other thing that we need to find the equation of a line is the slope of the line. And in this case the slope is not given to us, but of course we have a tool, the derivative. And remember, the derivative is the tool that allows us to calculate slopes of tangent lines anywhere on the curve. In this case we're looking for the slope of the tangent line where x is 0. So our job will be to find the derivative of y with respect to x, that is our derivative of this function, and then we need to evaluate that derivative at the x value 0. That will give us the slope of the tangent line that we're talking about. So before we go further, we need to know this slope amount. Well, we notice, as we've had in the past, that we have a product of functions. So we're going to think in terms of 2x as the first function and e to the x as the second function. So as we calculate, we'll say derivative of y with respect to x is the first function. See, we have it referenced over here, our first function, which is 2x, times the derivative of our second function, and our second function is e to the x, and of course its derivative is e to the x. And then we add to that the reverse. That is, we take our second function, which is e to the x, and multiply it with the derivative of our first function. Well, our first function is 2x, and the derivative of 2x is simply 2. Well, we've got some type of expression here. I suppose we could write this a little simpler. We could write this as 2x e to the x plus 2 e to the x. Now we could do some factoring and other things, but that's really not the issue. We're not really, the problem is not about finding the derivative. The problem is about finding the equation of a tangent line. And the reason we need the derivative is because we use the derivative to find the slope of the tangent line. So all that's really important for us at this stage is to take this derivative that we've calculated and evaluate it at the important x value. That's the x value for which we're looking at the tangent line, and that x value is 0. So we take our derivative and we substitute a 0 in for each of our x values, of course. And we calculate. Well, of course, 2 times 0 is 0, and 0 times anything else is 0, so we get a 0 result here. Now here we have 2 times e to the 0, and we remember that a number to the 0 power is 1 except for 0. 0 to the 0 power we don't discuss, but any other number to the power of 0 gives us a 1. So this is read 2 times 1, and of course we see that if we have 0 times 2 plus times 1, we'll get a result of 2. So that's the other important piece of information that we needed. kind of summarize real quickly here. We got this calculation of 2 from our derivative, and this point is going to be very important as we go through the next part to actually determine the equation of the tangent line. So we'll come up here. Now remember, to calculate the equation of a line in general, we can use what's called the point slope form, and that's read y minus y sub 1 is equal to m times x minus x sub 1. Now, we refer to the m as the slope of the line in question, and x sub 1, y sub 1 is a known point that is on the line in question, and we have both of those pieces of information, so we can substitute those values in. So we would simply replace y sub 1 with 0, which is the y value of our point. We'd replace m with 2, which is the slope of our tangent line. And then we would replace x sub 1 with the x value of the point that we know is on this tangent line. And then we would simplify, and we see that, of course, we have y on the left side. And since x minus 0 is just x, we have 2x here on the right side. And of course then, this is the equation of the tangent line in question. Now, before we go on, let me remind you that we can calculate the equation of a line a little differently. This is just as a reminder so that you can use the form that is most easy for you to remember. Any straight line can be written in slope-intercept form. That's what this is called. And of course that's ultimately what we had here. In our particular problem, we don't know the y-intercept, but the slope is given to us, or we have calculated, I should say. So we really know our line is going to look like y is equal to 2x plus b. Now, when you're trying to determine the equation of a line, what we end up doing is using the fact that we know one point that is on the line. And that means that if we use this x and y value into the equation of the line, that the left and right side have to be equal to each other, because that point makes the equation true. So we'll put our 0, this 0 in for y, and we'll put this 0 in for x, and that we know this resulting equation has to be true, and this resulting equation, of course, is just 0 is equal to b. And so this is implied and required of us for this point to be on the line that b has to be 0. So we can put that value b, and of course, into this position. And so our line then would read y is equal to 2x plus 0, or just y is equal to 2x. So we would have gotten the same result if we would have used a little different form of finding the equation of the line. This next example is going to be a little more thought-provoking. Let me state it here. Let's suppose we're given a function. Let's see, maybe a function like f of x is equal to 5x to the third power times e to the x times the sine of x. And we're asked to find the derivative of this function. Find f prime of x. Now, we clearly have a product, but we're immediately faced with the idea, I think you'll realize, that our product rule is a product of two things. And we see that we would immediately imagine of x to the cube and e to the x and sine of x, we'd really be thinking about three things, maybe 5x cubed. And so this presents a little bit of a dilemma for us. We don't really have a product rule that tells us what to do with the product of more than two things. So how do we approach a problem like this? What can we possibly do? It seems like we don't have a tool at all. Let me point out to you something that could be useful to you not only in this problem, but many problems in the future. Suppose we thought about 5x cubed times e to the x as being one function. Now, granted, we're going to have a little bit of trouble in a moment, but let's kind of think about that as being one function. We'll say u is 5x cubed e to the x. And then, of course, v would be our sine of x in this case. Now, to use the product rule, we have no trouble with the derivative of v. v prime, of course, derivative of sine of x is cosine of x. Our issues end up being when we go to calculate the derivative of u. And then we run into this idea, now that you see it, to find the derivative of u, we actually have to use the product rule. So in this problem, the way we've set it up, we're going to end up using the product rule in two different ways for the same problem. Well, let's see if we can't figure out the product rule by using this idea of first function and second function. So we're concentrating on finding the derivative of u right now. Let's think of the first function, in this case being 5x cubed, and the second function e to the x. We have a little bit of a problem because we're already using u and v, and all of a sudden we've got too many letters running around. So the way I'm going to do this is I'm going to say, okay, look, the way I'm going to find the derivative of u is I'm going to remember that its first function, 5x cubed, times derivative of second function, which is e to the x. That is, the second function is e to the x, and its derivative is e to the x. And then I'm going to remember that, oh, yes, now I say second function, which is e to the x, and I multiply that with the derivative of the first function. Well, here's the first function. Its derivative is 15x cubed. And now I can simplify u prime, we see, as 5x cubed e to the x plus, oh, except this should be a 15x squared, my apologies here, plus 15x squared times e to the x. Okay, we're finally ready to record the derivative of f. That's really what we were trying to accomplish. So the derivative of f is first function times derivative of second. Well, our first function was 5x cubed e to the x, 5x cubed e to the x. So its first function, 5x cubed e to the x, times derivative of second function. Well, in this case, second function sine x, its derivative is cosine x. Plus second function, say that's v, second function, here's the second function. So second function sine of x times derivative of first function. Well, here's the first function. Its derivative required us to use the product rule earlier, and the result we got using the product rule was this string. So second function is 5x cubed, a derivative, pardon me, of first function is 5x cubed e to the x plus, I keep making a mistake here, don't I? That's 15x squared from above. So plus 15x squared e to the x we've got a long, complicated string here. Now, we do see that we can do some distribution. We can distribute this sine x through that resulting derivative from earlier. So we could write this as 5x cubed e to the x cosine x as our first term, plus, now sine x times this first term would give us 5x cubed e to the x sine x, and when we multiply sine x with this second term, we would get 15x squared e to the x sine x. But we don't need, certainly don't need the brackets here. We've taken care of the brackets. Okay? Now, this is a long string. We could do some factoring. It's not necessary usually, but occasionally our book will have something factored and we'll want to double check our answer. So as we scan through each of these terms, we see 5 is a common factor, so we can factor out a 5. We see we have an x cubed, an x cubed, an x squared. We can factor out an x squared. We see each term has an e to the x factor, so we can factor out an e to the x. And then we would have what? Let's see, we would have an x cosine x in the as the first term, and we would have x sine x as our second term, and finally we would have what? 3 sine x as our third term. This might look a little cleaner. Probably either of these would be acceptable, though, as an answer. Well, that concludes the first part of the chapter on the product and quotient rule. We'll next look at the quotient rule.